What I'd like to do in this video is build off the previous video where we learned how to rotate a vector which is perpendicular to the axis of rotation. And what we're going to do is learn how to rotate vectors in general, rotate any vector through any axis. And along the way, we're going to derive what's called the Rodrigues rotation formula, which is a formula that uses vector analysis, that is dot products and cross products, to come up with a newly rotated vector. So we're going to do that, and we're also going to discover a Quaternion version of the Rodrigues formula, which I call the Quaternion rotation formula. We're going to see that the Quaternion rotation formula is actually much more compact than the Rodrigues formula, but both of them do the same job. They rotate any vector through any axis. Let me briefly review what we accomplished in the previous video. Suppose I have some plane here, which passes through the origin right there. What I can do is I can draw the normal vector with respect to that plane. Now this is the vector that sticks out of the plane at 90 degrees to the plane. And I designate it as n hat, the hat standing for the fact that the length of this vector is going to be assumed to be 1. So this vector sticks out of the plane at 90 degrees. And what we learned how to do was take any vector in this plane. Let's say I had that vector. Let me call it v. Now if this vector is in this plane, it's at right angles to n. Now suppose I wanted to rotate this vector v with respect to this axis n. Now I interpret n as a rotational axis. And let's draw in that newly rotated vector. Let's say it gets rotated by theta radians. And let me call the newly rotated vector v prime. What we learned and what we derived was that the way to get v prime was to take cosine theta times the original vector v and add that to sine theta times the cross product between n and v. So that's the formula we derived last time. As you can see, it was quite simple, and this takes care of any case where the vector that you want to rotate happens to be at right angles to the axis of rotation. We're going to build off that knowledge of rotating the perpendicular vector to rotate any vector. So let me go back to this picture with the normal vector in my plane. Now I'm going to assume that the vector is not on this plane. It's not at right angles to n. So let me draw it like that, for example, where this vector is off the plane. And again, let me call that vector v. Now, the fundamental insight to solving this problem is actually not too difficult to derive. What we're going to do is we're going to break this vector v into two parts. And to do that, what I'm going to do is I'm going to imagine projecting this vector onto the rotational axis. So when I project it like that, I get this vector which lines up with n. It's in the same direction as n. And I'm going to call this vector from here to there, that newly projected vector, v parallel. I'm going to use this notation with the two parallel lines standing for v parallel. And by parallel, I mean it's in the same direction as n. Now, you'll notice that if I have this vector, let's imagine I start at the origin. I go to that point right there at the tip of v parallel. If I consider the vector from here to here, this vector actually makes a right angle to the rotational axis. And furthermore, I can imagine moving this vector down here onto the plane. And this new vector, which is at right angles to the rotational axis, I'm going to call v perpendicular, or v perp for short. I'm going to notate it with that perpendicular symbol. So what I've done here is I've broken the vector v into two parts. One part which is parallel to the rotational axis and one part which is perpendicular to the rotational axis. So symbolically, what I have at this point is that v is the vector sum of v parallel with v perp. And hopefully you can see that geometrically. If I have this vector here, the v parallel, and I have this v perp right here, the v is the vector sum of those two vectors. The advantage to thinking of v as being composed of two parts, a parallel part and a perpendicular part, is that to consider the effect of rotation upon v, it suffices to consider the effect upon each one of these vectors individually. And to help understand what those effects are going to be, let me redraw this picture with fewer vectors on it. So let's have this vector be v parallel, which remember lines right up with n, our rotational axis. Let me have that vector be v perp. And now the vector sum of v parallel with v perpendicular, that was just v. So that's going to look something like that. There's v. And now let's consider rotating the vector v through this rotational axis, which lines right up with v parallel. And let's consider the effects upon each one of these vectors individually. First, what is the effect of rotation upon v parallel? Now, if v parallel lines right up with n, it won't be rotated at all. That is to say, symbolically, v parallel prime, the prime standing for the rotated version, is equal to v parallel. So that's the first observation. And the next observation is to realize that the only one of these two vectors which is changed by rotation is v perp. So let me attempt to draw that in like so. So I rotate by theta. And the newly rotated v, which is going to be v prime, is going to be the vector sum of v parallel plus this new vector, which I'm going to call v perp prime. So let me draw that vector sum in there. And that new vector from here to there, that's going to be v prime. Let's write that out symbolically. So I had v prime, which is going to be equal to v parallel prime plus v perp prime. And we made this observation that v parallel prime is equal to v parallel. So now I have that v prime is equal to v parallel plus the rotated version of v perp. So what that means is that if I want to find what v prime is, I just have to somehow compute what this new v perp prime is. And I also have to know how to project vectors. I have to somehow find what v parallel is in the first place. Here's what we have so far, that v prime is equal to v parallel plus v perp prime. And here's our concept of what's going on so far. We have our axis of rotation n. We have v parallel, which lines right up with it. And we have v perp right there. And the vector sum of v parallel and v perp is just v. And the v parallel is going to be eventually rotated. But what I'd like to do is take this vector and just move it right onto this plane here. Because remember, we have this normal vector, and we can always associate the plane to it, or a unique plane to it, once we say that the plane has to pass through the origin. So I'm going to move that vector down here to the plane, right there. That's the same vector, v perp. And remember that n makes a right angle with v perp. So now the question of what the rotated version of v perp prime is, well, that's just what we took care of in the last video. And to write that out, we're going to use the formula that we derived. So I have v parallel plus, and the formula just says that cosine theta times v perp plus sine theta times the cross product between n and v perp. Because we know how to do this already. We already know how to rotate a vector, in this case v perp, which is perpendicular to our axis of rotation. So I just plop in v perp instead of just v like we had last time. So that's all equal to v prime. Let me make a couple adjustments to this formula. So on the right hand side, I'm going to keep v parallel there for now. And what I'm going to do in the second term, cosine theta times v perp, is remember that v is equal to v perp plus v parallel. So what that means is that v perp is v minus v parallel. So I'm going to make that substitution in here. V minus v parallel. So that's the first substitution. And the second one is I'm going to realize that n cross v perp is actually the same thing as n cross v. And that's a short demonstration of why that's true. What I'm going to do is take the cross product between n and v. And remember, v is equal to v perp plus v parallel. And I can actually distribute this cross product like you would normally expect a product to behave. So I get that this right-hand side is equal to n cross v perp plus n cross v parallel. But remember that n is in the same direction as v parallel, so this whole thing is actually the zero vector. So I get that n cross v is equal to n cross v perp. So that's the justification for that substitution right there. Let me make just one more rearrangement here. Now I notice that I have two instances of v parallel. I have one right there, and I have one over here whose coefficient is actually going to be minus cosine theta. So I'm actually going to combine this term with that term there. And what I'm going to get is I have the 1 and then minus cosine theta. So I'm going to get 1 minus cosine theta all times v parallel. And then my next term is going to be cosine theta times v. So I have plus cosine theta times v. And then I have that last term, sine theta times n hat cross v. And that's still equal to v prime. Just rearranging the furniture a little bit. This is what we have so far, just moving this equation up to the top. And one last adjustment I'll do is I try to write everything in terms of just v's, n's, and thetas. So what I'd like to do is make a substitution for this v parallel part. Now remember, v parallel is the projection of v onto n, and that being that rotational axis. So that vector is going to be in the same direction as n. And to write v parallel in terms of n, it's just going to be as some scalar times n. And it turns out that that scalar, let me write this out, v parallel is equal to some scalar times n, because it's in the same direction. And that scalar happens to be the dot product v dot n. And this just comes from the projection formula for vectors. I would look that up if you haven't seen that before. So I can just make the substitution right into v parallel. So my final equation is going to be v prime is equal to 1 minus cosine theta times v dot n. Remember, v dot n is just a scalar, times n, that's the vector, plus cosine theta times v, and finally plus sine theta times n cross v. And this formula here is the Rodrigues rotation formula. As you can see, if I give you some v, some starting vector v, the rotation axis n, now remember the n has to be of unit length, so if you have some rotation axis, got to make sure it's of unit length, and some angle theta, you just plug and chug, just plug it right into this formula, and the output is your newly rotated vector v prime. And I claim this works for any vector, any axis. Let's do a bit of a sanity check here to make sure this formula makes some sense. Let's consider the case when theta is equal to 0. Theta is equal to 0. So that means the vector isn't really being rotated at all. Nothing's being done to it. So let's look at this first term. I'm going to have 1 minus cosine 0. So I'm going to have 1 minus 1, which means 0, which means this whole first term disappears. Next, I'll have cosine 0, which is 1. So I'll just have v. So far I have that v prime is equal to v. Then I'm going to have plus sine of 0. Now that's 0, so this whole term disappears too. So I just have v prime is equal to v, which is what you'd expect. Now let's consider the other case, or another case I should say, when v dot n is equal to 0. This means that the vector is perpendicular to the rotational axis. This is that whole case I spent a video on last time. Look what happens here. I have v dot n there, so this whole first term goes away, and I'll just have this term plus that term, which is precisely the formula that I got last time. So that makes a bit of sense too. So that's the Rodrigues rotation formula using standard vector analysis. Now let's do something non-standard. We're going to attempt to understand this problem from the point of view of quaternions, which is something we also did in the last video. So here's the picture that we've been thinking of, drawn over here. We have that insight that we had that V prime is going to be the sum of V parallel with V perp prime. And now what I'm going to do is I'm going to define up 5 new quaternions, where the scalar parts of these are going to be 0, and the vector part is going to be whatever it is. V, the quaternion V is going to be the vector V. V parallel is going to be the vector. It's going to have vector V parallel right there. And all the remaining 3 are going to be defined very intuitively. So what I'm going to do is I'm going to rewrite this equation using quaternions. So I'm going to have V prime is equal to V parallel plus V perp prime. Now, in the previous video, when we were talking about quaternions, we learned how to deal with this quaternion right here, this V perp prime. So what this is, recall, it's the rotated version of V perp with respect to n. And we call it V perp because it's perpendicular to n. So this is precisely the case we were talking about last time. And what we learned is that the way to deal with such quaternions is to multiply on the left by e to the theta times n, where n is that quaternion there. It's related to that rotational axis. So you multiply by e to the theta n times v perp. And this is equal to v prime. So this is actually the first quaternion rotation format I'd like to tell you about. And you can see it's very simple. Conceptually what you're doing is you're taking your initial vector v, you're breaking it up into 2 parts, as we've been doing. You're breaking up into a v parallel and a v perp. Now to get the newly rotated quaternion v prime, what you're going to do is you're just going to take the v perp and multiply on the left by e to the theta n. And that's it. Also notice in this formula that the v parallel is left unchanged, whereas the only thing that's being operated upon is the v perp, which is being multiplied on the left by e to the theta n. And that lines up very nicely with what we've been conceptualizing here in our picture, that the v parallel is left unchanged and the v perp is the only vector being rotated here. Now let me rewrite this formula, expanding out the e to the theta n using Euler's formula. So this rotation formula using quaternions can be written as v prime is equal to v parallel plus, now let me expand out the e to the theta n using Euler's formula. So the scalar part of this new quaternion is going to be cosine theta. Then I'll have plus sine theta times the x component of the normal vector times I. Then I have plus sine theta times the y component of the normal vector times j plus sine theta times the z component times k. So this whole thing is e to the theta n. As you can see, it's usually preferable to write it in this compact form, but here's what it looks like, just for clarity. And this is all going to be multiplied by v perp. There's actually a more compact way to write this quaternion rotation formula. And to show you what that compact form is, I'm going to have to prove a couple of facts about these quaternion exponentials and their relation to either v perp or v parallel. And the first one I'd like to prove to you is that e to the theta n times v perp is equal to v perp times e to the minus theta n. Now remember, this is significant because quaternion multiplication does not commute. So in this case, if you want to commute these 2 quaternions, you can do so, but you're going to have to stick a minus sign up there. In other words, you're going to have to take the conjugate of this quaternion here. And this can be verified just by a simple calculation. Let's write everything out, starting with the left-hand side. So what is e to the theta n? I'm actually going to write this in a more compact form, the scalar vector form. So the scalar part is going to be cosine theta, and the vector part is going to be sine theta times n hat. That's that first quaternion. Now v perp is just 0 v perp. And then on the right-hand side, I have the same thing, 0 v perp. times, now in this case, I'm going to have cosine of minus theta first, but cosine minus theta is just equal to cosine theta, because cosine is an even function. So that's a scalar part. And now I'm going to have sine of minus theta, but sine is an odd function, which means the minus sign can come out front. So I'm actually going to have minus sine theta times n. Now let's multiply out these quaternions. So let's find the new scalar part of the left-hand side. So the scalar part is going to be cosine theta times 0 minus the dot product between these two vector parts. So far I'm going to have 0 minus the dot product of this vector part with this vector part. But notice that n is perpendicular to v perp. So that means my new scalar part for the left-hand side is actually going to be 0. And if you look at the right-hand side, it's also going to be 0. So my new scalar parts are going to be zeros. So far so good. The quaternions are equal in their scalar parts. Now the new vector part, I'm going to have cosine theta times v perp. So cosine theta times v perp. I'm going to have 0 times this vector here, which is just 0. Then finally I'm going to have plus the cross product between this vector and this vector, which is going to be sine theta times n cross v perp. And that's the new vector part of the right-hand side, this whole thing. Of the left-hand side. Now, let's calculate the vector part of the right-hand side. So I'm going to have 0 times that vector there. That's going to be 0. Then I'm going to have cosine theta times this vector. So I'm going to have cosine theta times v perp. And then I'm going to have the cross product between this vector and that vector in that order. So this can be rewritten as minus sine theta times v perp cross n hat. Now, if you have a look at these two cross products here, I have n cross v perp, and here I have v perp cross n hat. Now, when you switch the order of the cross product, you have to stick a minus sign in there. So I could actually rewrite this vector right here as minus sine theta, sticking the minus sign out front, times v perp cross n hat. And as you can see, once I make that observation, that this is equal to this, then I get equality between left and right hand sides. So I have the proof that e to the theta n times v perp is equal to v perp times e to the minus theta n. So that's the first fact that I wanted to prove. And the second one is going to be the following, that e to the theta n times v parallel, this time, is equal to v parallel times e to the theta n. That is to say, e to the theta n commutes with v parallel. Now, to show this statement, I'm going to review a concept that I've shown in one of my previous videos called the commutator. Now, if I have two quaternions, let's say a and b, there's this thing called the commutator between a and b, which is a fancy way of just saying ab minus ba. Now, if the commutator between two objects is 0, let's say this is equal to 0, that means that those two, the a's and the b's, that they commute. That AB is equal to BA, if it's true that AB minus BA is equal to 0. Now, it turns out for the quaternions, let's say A and B are two quaternions now, that the commutator between two quaternions is 2 times the cross product between the vector parts of the quaternions. And now, if you look at what the vector part of e to the theta n is, the vector part is going to be sine theta times n hat, and the vector part of this is going to be just v parallel. However, n is in the same direction as v parallel, so that means that this cross product is actually 0. So I do actually get the case that the commutator goes to 0, which means that these two quaternions commute. With those two facts in hand, I can now write this formula in a much more compact way. And to do it, it's actually quite simple. I just have to invoke a couple dirty little tricks. Now, with v parallel, let's look at v parallel. Out in front, we're multiplying by 1. But the number 1 can be written in a number of different ways. And the way I'm going to write the number 1 is actually e to the theta over 2 times n times e to the minus theta over 2 times n, and then times v parallel. As you can see here, when I take the two arguments and add them together, I just get 0, and e to the 0 is 1, so I haven't changed anything so far. So that's the first little trick. And the second trick is going to be rewriting e to the theta n as e to the theta over 2 times n times e to the theta over 2 times n, and then times v perp. So you can see here that when you add the arguments here, you get theta times n. So I haven't changed anything there. Now I'm going to use those little tricks, those facts that I just proved. Now I'm going to look at e to the minus theta over 2 times n and v parallel. Now I know those two quaternions will commute. So I'm going to rewrite this first quaternion as e to the theta over 2 times n, then v parallel times e to the minus theta over 2 times n. And now I'm going to look at this quaternion and this one. Now what I've just found is that when I commute those two, I'm going to have to stick a minus sign there. So I actually get plus e to the theta over 2 times n v perp times e to the minus theta over 2 times n. Now look at what's going on here. I have two quaternions, the v parallel and the v perp, both being multiplied on the left by e to the theta over 2 times n, and both being multiplied on the right by e to the minus theta over 2 times n. So what I'm going to do is a little bit of factoring. I'm going to write v parallel plus v perp. Then I'm going to write multiplied on the left by e to the theta over 2 times n, and multiplied on the right by e to the minus theta over 2 times n. And finally, what is v parallel plus v perp? That's just plain old v. So I'm going to rewrite this as e to the theta over 2 times n times v times e to the minus theta over 2 times n. And that's v prime, the rotated version. And that's the compact way of writing the quaternion rotation formula. What's nice about this compact quaternion rotation formula is that you can start calculating immediately if you know v. You don't have to worry about breaking it apart into v parallel and v perpendicular. In fact, you don't even have to know how to calculate v parallel or how to do projections or anything. You can just do this computation. And I'd like to rewrite this in yet another way, just expanding out the e to the theta over 2 times n, just so it's absolutely clear what that quaternion exponential actually is. And people who've done rotations with quaternions are going to recognize this. So e to the theta over 2 times n is going to be cosine of theta over 2. That's going to be the scalar part of the quaternion, plus sine theta over 2 times the x component of the normal vector times I, plus sine of theta over 2 times the y component of the normal vector times j, and then plus sine theta over 2 times the z component of the normal vector times k. So that's what that quaternion exponential is going to look like. And correspondingly, e to the minus theta over 2 times n, just putting the negative signs in where they need to be placed, I'm going to have cosine of minus theta over 2, but that's just equal to cosine of theta over 2, because cosine is an even function. Now, here, here, and here in the signs, remember sine is an odd function, so I can yank the minus sign right out front. So I can actually write minus sine theta over 2 times the x component of n times I, and the remaining two components are very similar. Minus sine theta over 2 times the y component of n times j, then minus sine theta over 2 times the z component of n times k. So in summary, if you have some vector v, you write it as a quaternion v. You're going to multiply on the left by this quaternion here, and then multiply on the right by this quaternion. And by the way, this quaternion down here is the conjugate of the quaternion here. So I could also rewrite this formula as this. Let's define this quaternion to be q. And then this one would be the conjugate of q, or q star. So this formula could also be rewritten, where q is understood to be this quaternion here, that v prime is equal to q v q star. There tends to be a lot of philosophizing on the internet why this theta over 2 appears at all. After all, we're trying to rotate by theta, not theta over 2. So why should we be getting things like cosine theta over 2 or sine of theta over 2? And combined with the fact that we're talking about 4D space, a lot of people get interested in high dimensional spaces, so they smoke a little dope and they say, yeah, man, this rotates by half, this rotates by half. I'm not sure what that means, but I prefer to view the algebraic consequences of what's going on here. That is, let's suppose v is parallel to n. So if you're rotating a vector which is on the rotational axis, after all, that's the only way that v can be parallel to n, and they both pass through the origin. So what we expect is that v prime should be just equal to v. Now, we've seen that if v is parallel to n, then I can actually commute these two quaternions. So I'll get e to the minus theta over 2 times n, then e to the minus theta over 2 times n. And those combine to give you e to the 0 times v. So that means that I indeed get v prime is equal to v. So that's one nice case. The other nice case is that, let's suppose that v is perpendicular to n. Now we learned that when v is perpendicular to n, these two can be commuted, but you've got to put a minus sign in there. So what you actually get is the positive right there. So you get e to the theta over 2 times n times e to the positive theta over 2 times n, then times v. And then those two combine to give you e to the theta n times v. That's equal to v prime. And that, as we've seen before, is a good rotation formula. That one actually makes some sense, and it's very similar to the complex numbers. So hopefully you've enjoyed this tour de force of three-dimensional rotations, understood from the point of view of standard vector analysis, which gave us that Rodrigues formula, and from the point of view of quaternions, which gave us this quaternion rotation formula involving quaternion exponentials. So if you enjoyed the video, I encourage you to subscribe to my channel, like the video, leave your comments, especially angry ones. And I'm looking at you, that mushroom asshole that left a comment on my other Quaternion video. How dare you? I've never heard such filth in my life. And as always, I thank you for watching and 400 plus subscribers.